Hello. For our final project, we have created a comparative analysis of concurrency models in Python. I'm John, and my role was multi-threading.
And I'm Gil. My role was integration and testing.
I'm Cassandra. I did multiprocessing.
I'm Michael, and my role is async IO workloads.
I'll give a quick overview of our project. We designed, implemented, and evaluated multiple concurrency models using a standardized set of workloads. To compare them fairly, we built a benchmark suite that runs the same tasks across multi-threading, multiprocessing, and async IO. We measured how each model performs under CPU-bound and IO-bound conditions and analyzed the trade-offs in speed, scalability, resource efficiency by looking at metrics like latency, throughput, and resource usage. Next, we'll walk through the specific workloads in our experimental setup.
For this part of the design, we chose four execution models that map directly to the concurrency mechanisms we studied during the semester. We start with the sequential, a single thread of execution as our baseline. Next is multi-threading, which ties directly to GIL or the global interpreter lock in Python, and shared memory threading. We did multiprocessing, which connects topics surrounding multi-core parallelism and process isolation. And then finally, we did async, which reflects the non-blocking input-output systems that we covered. These models cover a variety of topics covered in the course: performance, shared memory, true multiprocessing parallelism, and event-driven async.
And here's a diagram of how our code is organized. We have multiple ways to run it, from Python command line arguments to individual runs with a YAML file containing parameter values. Both are ways to invoke the bench runner, to sweeps over multiple values of any given parameter, also in YAML files, invoking the experiments run sweeps module. And those entry points then invoke any of the four models, which in turn run any of the four workloads. And for the tests, we have uh, test code runnable via PyTest that discovers all the YAML files and executes them. This served as a regression suite during development and branch merging to ensure that code didn't break. If the executions passed, we would then spot check the CSV files and graphs.
Here we're looking at how memory usage changes as we increase the number of multiprocessing workers for matrix multiplication. What we see is almost perfectly linear growth, roughly 25 megabytes with one worker, around 50 megabytes with two workers, and close to 95 megabytes with four workers. This matches exactly what we learned in class about process-based concurrency. Each process has its own address space and its own copy of the working data. There is no shared memory by default, so memory scales with the number of workers. This graph shows the cost of multiprocessing. We get parallel speed up, but we pay for it with increased memory usage. Next is wall clock time, which drops significantly as we add more workers. With one worker, the matrix multiplication workload takes the longest, and with four workers, we see roughly a 3 to 4 times speed up. This is exactly what we expect for a CPU-bound task when using multiprocessing. Each process runs independently and bypasses the GIL, so we get true multi-core parallelism. In other words, more workers directly translates to less wall clock time. This matches the parallel scaling curves we talked about in class when discussing multi-core efficiency. G-flops measures how many billions of floating point operations per second we're achieving. In simple terms, it's a direct measure of how much math the system is doing per second. What's important here is that G-flop scales almost linearly with the number of multiprocessing workers. That tells us the workers are not stepping on each other. They're actually increasing total computational throughput. This reinforces that multiprocessing is the correct model for CPU-bound numerical workloads. Meanwhile, the G-flops for threads, async IO, and sequential models stay completely flat. Threads can't bypass the GIL, and async IO is single-threaded, so neither can take advantage of the multiple cores. When we compare all the models directly, the results line up cleanly with what the course taught us. Multiprocessing is the only model that reduces wall clock time for matrix multiplication. Threads do not get any faster as we add workers because the GIL prevents parallel execution of CPU-heavy code. Async IO also stays flat because it's designed for non-blocking input-output, not computation. Sequential remains our baseline, so this graph makes the core point of our CPU analysis. For compute-heavy tasks like matrix multiplication, multiprocessing is the only model that meaningfully improves performance.
Now I'm going to walk us through the results for our async IO experiments, beginning with our experiment on wall clock time. So just follow me to the left side of this graph. That's our wall clock time on the y-axis, and on the x-axis, we're seeing the number of workers growing. So on this plot, lower is better because we want things to run faster. So beginning by looking at the sequential model in green, we can see that this can run 80 reads of the example CSV file in all on a single thread. So it makes sense that that would be slower with the just the single example. But once we get to two workers, we can actually see that the async IO begins to be faster than the sequential runner. And that property stays the same until we get up to 16 runners, and we can see that the gap begins to close and the async IO is not so much faster than the sequential runner. And that suggests that the overhead of spawning the extra threads that the async IO runner does is not worth the extra file reading that it is performing. On the next slide, we will see the same property. So you can see in the bottom, the multi-threads runner is extremely slow because it is doing so much multi-threading overhead that it is wasting CPU cycles instead of reading in file data. Now, on the sequential and async IO, at the top of the graph, we see the same result, that there is this Goldilocks zone where throughput does increase in the case of async IO, but after a large number of workers, we see that the overhead of creating all those workers causes sequential to actually have higher throughput. Next slide, please. So in a final example, I looked at the difference between reading a compressed columnar file format, Parquet, versus just reading CSV format from disk. And in our experiment, reading an entire table of data is 10 times faster when we are using the compressed format that uses columnar storage. And when we are using uh, Parquet's projection feature to just read a single column, it is up to 24 times faster because Parquet is able to store the data with good data locality for the columns. Next slide.
So I'll give you a brief update on our goals. So we finalized our system and built our sequential baseline workloads, then implemented our threads and multiprocessing models, ran our experiments by sweeping input sizes, and our async IO model and its experiments were complete. And we also finished a parameter sweep comparing local files in Apache Parquet. What's left is our hybrid experiment stretch goal, which is compiling and analyzing all collected data and running a CPU experiment using Spark, and then finishing our final report. Overall, the core experiments were finished, and our remaining work focuses on synthesis, hybrid testing, and final deliverables. Our main stretch goal is centered on a hybrid integration that chains threads into multiprocessing and then into async IO, using about 10 sample files to exercise the full pipeline. The async runner would write outputs to files to simulate a database and let us validate basic throughput. We weren't able to complete this work due to the complexity and time constraint, but it's a clear next step. Those improvements would help us make stronger data-driven recommendations.